Good morning, everyone who just joined. How are you guys doing today? I'm doing very well. Thank you, Obi King. So, have you guys watched the? Have you went through the notes or the videos of this week's work? And how are you finding it so far? Do you understand the reactions? Will you be able to calculate the average rate of reaction? Will you be able to calculate the rate? Will you be able to explain the collision theory? How are you guys finding the this topic so far? I don't think I'm completely able. So you still have some other things that you don't understand? Okay. Okay, and what are those things of a king? So that maybe we can focus on them or clarify them. When it comes to calculating, I'm lost. Okay, okay, I see. I think we need to do some example, some example today, and see if you will be able to understand maybe how to calculate the average rate of reaction by the end of this lesson. Morning, morning, everyone who just joined. I hope you guys are good today. So, today we're continuing with the rate and extent of reactions. And I have a question for you guys. Do I explain the Maxwell Boltzmann's equations or curve distribution curve, or we do some examples? Do you understand how the Maxwell's Boltzmann's curves work, or how you can explain them in terms of temperature, in terms of the concentration? Or must we do more examples? Guys, what do you think? Do we do more examples? No, I don't understand the curves. Others, what are you saying? Overking, Jade, Talent, what are you saying? Do we explain? Yes, more examples. Overking, do you understand the curve, the Maxwell Boltzmann's curve? I'm a bit lost with the Maxwell's curve, but if we don't do them now, we will do them later stage. Okay, I think we can just cover them and then we'll do more example, because at the later stage we can have time to do more examples. Then for me to start explaining the graphs, well, we need to do examples that need us to apply the graphs. So okay, great. I'll start by explaining this, and over King we will do more questions or more examples. So, but we need to understand the theory behind for us to answer some of the questions. As in our last lesson, I explained the potential energy diagrams about the endothermic and exothermic reactions and how they work. But now we need to talk about the Maxwell-Boltzmann distribution curve. So what basically happens here, so you have a gas mixture. In a gas mixture, right, let's take you have a beaker and you have a certain gas mixture which is in an inert environment or something like that. So in a gas mixture, all the molecules, they are constantly moving, and they move at a specific temperature. When the temperature changes, there's something happens, and the particles have speed and kinetic energy. So we really need to explain that. So a mixture containing different gas molecules can be put in one beaker. So what happens basically with Maxwell-Boltzmann distribution is for you to be able to explain what happens in a gas mixture when you have particles in that beaker. You know that those particles are constantly moving at a specific temperature, and some have kinetic energy that is different from other molecules. So with Maxwell's Boltzmann distribution curve, it will help us to explain that. So I have 3 diagrams here. I hope you'll be able to see it clearly. It's not too small. I have 3 graphs, but I'll start with the first one. So this is a Maxwell-Boltzmann distribution curve. So in this curve, you have particles. Remember, I said you need to picture that you have a beaker and you have different gas particles inside the beaker. Now you must be able to explain what happens in this. So the curve, as you can see, there is a curve that goes through the origin. What does it mean? It means that because no particles have kinetic energy being equals to 0. So in a beaker, it means that the particles, they have energy. As you can see from here, the curve start from the origin, which means that there is no particles that have 0 kinetic energy. That's point 1. And the second one, you have your kinetic energy and you have your the number of particles with a given, this is the number of particles with a given kinetic energy. So this part represents how many particles with that certain kinetic energy is. And in here, this is the amount of the kinetic energy of the molecules or the particles in the beaker. So we have said that the curves start from 0 because in the gas mixture, there is no particles that have 0 kinetic energy. And the graph, the area under the curve, it represents the total number of particles in that system. So this area right here, it represents the number of particles that are in that particular system. As you can see, the graph with the curve does not touch the x-axis in this side because there's always a small fraction of particles with a very high kinetic energy. So the kinetic energy increases as you go to the right. You know how the x-axis work, that when you go to the right here, it means the particles were highlighted by yellow, they have a very high kinetic energy compared to the particles that are found in this case. And what does the peak of the graph represent? The peak of the curve, it represents the most particles that have the same kinetic energy. So you see from here to somewhere here, it means that the particles, most of the particles in that gas mixture, they have the same kinetic energy. But in this case, from here, this is the activation energy. It means that there are some a small fraction of the particles with a very high kinetic energy. And as you can see, this fraction, it means that the kinetic energy is greater than the activation energy. So this is the simplest curve, the Maxwell-Boltzmann distribution curve, without us talking about if it has temperature, one temperature. So now what happens if the temperature is increased from T1, as you can see here we have T1 to T2, what will happen to the distribution curve? It's the same graph, but something will happen. As you can see, T2 is not the same as T1. So what happens? One thing that you need to take note of, we spoke about the area under the curve. So you must always speak about the area under the curve. The peak of the curve, you must mention something about the peak. You must mention the kinetic energy of the particles. And for the temperature, so in this case, the area under the graph remains the same. As you can see, the area under the curve remains the same for T1 and T2 because the number of the particles in the reaction mixture remains the same. As you can see, when the temperature is increased, the area under the curve remains the same, which means the particles are the same. But the peak is wider to the right. As you can see, it shifted to the right. It means something. What does it mean? It means that because more particles, they have higher kinetic energy. So as the T2 is increased, as you can see, it means that more particles will have more or higher kinetic energy. And what does this mean? It means that there will be more particles with kinetic energy greater than the activation energy. And as you can see in this case, there is more particles with more higher kinetic energy that is greater than the activation energy. And what does this mean? It means that there will be more effective collisions. And what does it mean? At T2 there will be higher reaction rate. Any questions so far, guys? Do you understand? Any questions, guys? So you understand how T1 and T2, like the other one, shifted. Is there someone who wants to talk? Yes. This one, T2. Yes, the temperature has now increased. Okay. Another question, guys? Okay, now let's go to the concentration. What happens if the concentration of the liquids is increased from C1 to C2, or the pressure of the gas is increased? What happens to the distribution curve? As you can see, with the concentration, when it's increased, the peak is higher than the normal distribution, or the first concentration, or the normal concentration of the gas, or the pressure of the gas or the liquid. And the area under the curve is greater because there will be more particles per unit volume in that container. And what does this mean? It means that at C2, more particles have kinetic energy greater than the activation energy than at C1. As you can see, here is C1. C1 only have this part. This has that small fraction of particles with kinetic energy greater than the activation energy. But when the concentration or the pressure is increased, you can see that there is more particles than in C1. And what does this mean? It means that there is more effective collision per unit time. Hence, there will be a higher reaction rate. So what does this mean? It means that the concentration is greater than C1, and here the temperature too is greater than C1. So basically, what's important with the Maxwell-Boltzmann's curve, you must be able to mention the area, as I've said, the peak, the kinetic energy being greater or less than the activation energy, And the last two things to confirm, you must talk about if they have more effective collisions or not, and that how does that affect the reaction rate. Does increasing the concentration affect the reaction rate? Yes, the reaction rate becomes higher. The same with the temperature. When the temperature is increased, the reaction rate becomes higher. Any questions, guys? Do you understand? So the question can come in a way like this: what happens if you decrease the concentration? Now you must be able to explain that in terms of the Maxwell's distribution curve. So if you understand what happens when it increases, you must be able to explain it when the concentration decreases or when the temperature decreases. Yeah, any questions? Chloe, do you understand now? Yes, I'm saying, do you get an idea of this? Okay, great. Any other questions, guys? Oh, my gang, are you okay now? Yes, so okay, let's give an example with the concentration. If they say, explain what will happen to the Maxwell-Boltzmann distribution curve when the temperature is decreased. It means that the peak will be smaller than C1. The peak of C2, which is the decreased, will be smaller than C1. And it will mean that the area under the curve is less than that of C1, hence there is less particle in the container. And hence C1, which is the one will be higher than C2, will have more particles that are greater than, it will have more particles with kinetic energy greater than activation energy than those that have the decreased concentration. Hence, there wouldn't be a lot of effective collision and the reaction rate will decrease. So that's how you just reverse everything you will explain when the concentration is increased. Do you understand it now? Yeah, so guys, will you be able to explain these graphs if you had to get a question in any way? I hope so, that you will be able to explain this, because it looks simple when someone is explaining it until you have to tackle a question with such. But I think with practice and doing more examples and going through the theory of these graphs, it will be easier. I feel like I just need to work with it more. Yes, true. You just need to like sit down with it and just don't do it a day after before you write, or when you just need to go write, because it's easy for you to forget the important things. It's very easy for you to forget the smallest details of everything. So you just need to spend more time on them. So now let's do an example of the average rate of reaction, that you must be able to calculate the average rate of reaction. So this example say iron reacts with oxygen as shown in the balanced reaction. You have iron plus oxygen that gives iron oxide. So you have 2 grams of iron and 0.57 grams of oxygen and are used during the reaction. 2.6 grams of iron oxide is produced. The reaction takes 30 minutes to go to completion. Calculate the average rate of reaction. For A, the use of iron, B, the use of oxygen, and C, the formation of iron oxide. So I think maybe we'll be able to answer A. So let's start with A. What are we given? I hope you remember the rate of reaction equation. As we've explained in our previous with the graphs, that you can be able to explain the reaction rate of or what happens to the reaction rate by using graphs, but sometimes in this case you can get an equation or a reaction. You must be able to calculate something, or you must be able to calculate the reaction rate. Like in this case, you need to calculate the average rate of each of the reactants in the product in that reaction. So you must be able to do that. So now we're going to start with A. We need to calculate the average rate of reaction for the use of iron. And what are we given from iron? We have 2 grams. We're given the mass and the time. We are given the mass of oxygen. We're given the mass of the product. So now we have the mass. What can we find from iron? We can calculate the number of moles. So the first thing you can do in this case is to calculate the number of moles. Number of moles divided by the molar mass. What is the molecular mass of iron? It's in the periodic table. It's going to be 55.8 grams. It's 55.8 gram per mole. Now from this you can substitute your 2 gram that you have been given of iron, divide by 55.8 gram per mole. And the answer, what is the number of moles of the iron used? You're going to get 0.0358 mole. Ma'am, if you use 56 gram, is it wrong? No, it's not wrong. It means that you would have converted this one. But I'll encourage you, like when, like for an example, use it as it is given. So if it's 56, use 56 if that periodic table is like that. So it wouldn't be wrong. But that could be tricky because you'll find that your answer it's rounded already. So I'll say use it as it is. So now since we've calculated the number of moles, we need to calculate the rate of reaction. And we know that the equation of the rate of reaction, it says the rate of reaction equals to the number of moles divided by the time. So we're given 30 minutes. And we need to convert 30 minutes into seconds. And what is going to be that? Now we need to calculate the average, or just write average rate of reaction. What is 30 minutes in seconds, guys? Of iron. And you're going to have, it's going to convert 30 minutes, you're going to times by 60 seconds, you're going to have 1800. So now we know that we'll have number of moles of iron divided by the time given for us to get the average rate of reaction of iron. So we know that we calculated our number of moles to be 0.3558 moles divided by 1800 seconds. And what is going to be the average rate in this case? It's going to be 1.99 times 10 to the power negative 5 mole per second. So now you've calculated the average rate. Yes, the answer is 1.99 times 10 to the power negative 5 moles per second. Per second, the unit, don't forget. So now you've calculated the average rate of ion, the use of ion. So it takes this reaction rate for it to use ion. And we need to do the same with B. So now that I've shown you the step, you do the same thing with B. You first calculate the number of moles. You have the time, so you just divide the time. You just divide the number of moles by the time, and you get the average reaction rate. The same with the formation of an ion. But with iron, you will need to calculate for the molar mass, since you have iron plus oxygen. And then you calculate the number of moles and you calculate. So even in B, you will have to calculate the number of molar mass. You have your mass, you have your molar mass of, you have to calculate what is 16 times 2 is, yes, the time is the same. Remember, this is the same reaction. So the time is the same for all three because they're undergoing the same reaction. Any questions, guys? Do you understand? And then with the average reaction rate, you will have, in this case, the same. Now you will have the number of moles of oxygen divided by the time, and you get your answer of the average time. Same with C, but ma'am, when I calculated, I don't get that. What do you get, Chloe? How do you calculate? Remember, converting 30 minutes into seconds, you have to multiply by 60 seconds. What is the mole amount, ma'am? Wait, for the time for you to convert 30 minutes, you have to convert it into 0. that. And the number of moles that we calculated is 0.358. Is that what you get? 0.358. Is that what you get, Chloe? Oh, okay, but now we're getting the same answer. Okay, great. Any other questions, guys? Will you be able to calculate for the other reactions? So this is how you calculate the average rate of reactions. Any questions, guys? Any questions? Okay, so guys, if you don't have any questions or any comment, I think we'll end our lesson here today. And I'll encourage you guys, when you're doing the homework or you're doing any questions and you feel stuck, please feel free to text me and ask me. So don't sit when you don't understand anything. Even with the graphs, if you don't understand them, please let me know. so that I can help you. But if you sit and keep quiet and don't ask, that's not a good idea. So if you guys don't have anything today, so bye everyone. I will see you guys in our next class.